Welcome! In this video I will show you how to solve problem 4.13 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now this problem states the following. It has three parts. So part A, we have to find the expectation value of r and r squared for an electron in the ground state of hydrogen. And we want to express the solution in terms of the Bohr radius A. We also want to find the expectation value of the Cartesian coordinates x and x squared for the electron in the ground state of hydrogen, okay? And in part C, we want to find the expectation value of x squared in the state n equal 2, L equal 1, m equals 1, okay? So let's do this just step by step. So part A, we want to find the expectation value of two different powers of r. So it could be useful, and it will be useful, to just see this in general just a little bit. So the expectation value of r to some arbitrary power n, this is simply the integral from 0 to infinity of our wave function squared, so 1 over pi a cubed e to the minus 2r over a. And then we have r squared, right, coming from the fact that we're going to be doing the integral in spherical coordinates, right? So sine theta, right? And then we have to include 0 to 2 pi and 0 to pi. So in this case, I need dr, d phi, d theta. Okay, so that is what we want to integrate. And of course, since we are doing r to the n, we cannot forget about r to the n. I almost forgot about that. Don't forget about that. So this basically means we have to integrate r to the 2 plus n. Okay, maybe I'll just write it a little bit neater here. So r to the 2 plus n. That's what we want to integrate. Okay, so what is this? Well, here there are some things that we know, right? I mean, the integral of sine from 0 to pi is 2. The integral from 0 to 2 pi is 2 pi. So we have a factor of 4 pi as usual. Right, simply integrating sine and basically over the angles. I'm just going quick over that because we have done it so many times, and it's simply the integral of sine. So I hope that you can do that. If not, let me know. And then we have e to the minus 2r over a, r to the 2 plus n dr. Okay, so this is the integral that we have to solve in the cases where, we have to find this expectation value. And we know what this integral is. We have solved it repeatedly on this channel. I will give you again the idea and the notion how you can solve it. So whenever you have an integral, maybe I'll change colors here. So whenever you have an integral that is of the sort 0 to infinity of r to the, let's say m here, e to the minus, let's say br dr, then what you do here is you simply put a new variable. You say z is going to be br, dz is going to be dr times b, and then you plug it in. So we get 0 to infinity, and then instead of r, you have z over b, right? You would have z over b to the m, and then e to the minus z, and instead of dr, you have dz over b. So as you can see, we get 1 over b to the m plus 1. And then we have to integrate between 0 and infinity of z to the m, e to the minus z dz. And this integral you can solve by integrating by parts. And you have to do an integration m times, right? So let's say that u is going to be z to the m, du will be m z to the m minus 1 dz, and then dv we can choose to be e to the minus z dz, and thus v is simply minus e to the minus z. So with this, the integral that I will label m, because this is the integral when the power is m, right? Or rather this, because this integral is actually just this part. So this is im. So this is, first we multiply these two together, so minus z to the m, e to the minus z, evaluated between 0 and infinity. Now, this is 0 at both of those points because z is 0 at 0 and e to the minus z is 0 at infinity. So then we only have minus the second part, which is minus this times this. So we get plus integral from 0 to infinity of m, which we can write outside. So let me get rid of this. So we get m times the integral z to m minus 1 times e to the minus z dz. And notice this is exactly the same as before, except that now we have this little factor of m in front, and we have decreased the power by 1. So basically this is m times the integral of m minus 1. So if we do it again, we would get m times m minus 1 integral of m minus 2. And we can go on, all the way until we get to the point where we are at, so m minus 1, m minus 2, etc., until we get all the way to the integral m minus m, right? Which would be 0 to infinity of e to the minus z dz, which is simply minus e to the minus z between 0 and infinity, and that is simply 1. So what this is then is simply, so this integral right here, which is what we have been solving, this is simply m factorial. So this is simply m factorial, m times m minus 1, m minus 2, m minus 3, m minus 4, all the way to 3 times 2 times 1. Okay, so this is the result for these integrals. Now, using this in this particular case, this is a very useful formula for you. That's why I always like to derive it for you. So this integral then, what is it? Well, we have 4 pi, well, the pi's cancel out actually. So 4 divided by a cubed, and then we have 1 over b to the m plus 1. What is b? B would be 2 over a. So we have 1 over b, so we would have a over 2 to the m plus 1. Now, what is m in this case? It's 2 plus n, so we have 3 plus n. And then we have 2 plus n factorial, so 2 plus n factorial. Okay, so that's the result in general. Now, what about, some particular case? So now let's go for actually the 2 cases that we care about. So this is r to the n. So let's now calculate just r, the expectation value of r. So this would be 4 over a cubed times, and now we have n is 1. So we have a over 2 to the 4th times 3 factorial. Okay. So this would be, let's see, so that is, this is a to the 4th, so we have a, then we have, that's 32, right? 2 to the 3rd is 8, so that's 16. So we have 4 here, 16 here, and then 3 times 2. So 4 times 2 here is 8, so these leave us just 3 over 2. So this would be 3a over 2. And now using the formula for r squared, this would be 4 over a cubed, and then a over 2, 3 plus n, now n is 2, so we have 5, 4 factorial. So this time we have, let's see, so 4a squared, 2 to the 5th, this is 32, and then times 4 times 3 times 2. So this is 16 times 2, that's 32. So this and this and this, they give us 32. So we are only left with 3a squared. And that is the expectation value of r squared. So you can see that deriving the formula was actually quite useful to us. Now the next part that we want to do is here, part B, find the expectation values of x and x squared for an electron in the ground state of hydrogen. Okay, so now there's a few ways to go about it. We're going to try to do this as smartly as possible. So let me perhaps select the wave function and take it with me. So wave function, come with me. Okay, now we want to find the expectation value of x. What does that mean? That means that we want to, in our integral, right, from 0 to infinity, and we also have, okay, so I said one thing, wrote another. So we are integrating over all of space. So 0 to 2 pi, 0 to pi, 0 to infinity of. Now our wave function squared here, so 1 over pi a cubed e to the minus 2r over a. And now we have r squared sine theta. And now x, right? X, the r, in this order, it's theta and then phi. Okay, but we are integrating over spherical coordinates and we just put a Cartesian coordinate in there. So that is very confusing unless we keep in mind that x is equal to r sine theta cosine phi. So if we do that, we get r cubed here, sine squared here, and cosine phi. Now this would be a very, not that much of an annoying integral, but there are some slight changes. So first of all, notice here that we have to integrate over cosine, and that's, oh, red flag, because we have to integrate 0 to 2 pi of cosine of phi d phi. This gives us minus sine of phi between 0 and 2 pi, and guess what? This is minus 0 minus 0. So this integral is 0, which means that the entire thing is 0. So the expectation value of x is 0. All right, great. So that is the first part. Now let's go for the expectation value of x squared. So this is, well, quite similar to what we had before. Let's maybe go back here. Right, I'm gonna use what we have already written down. Right, so let's go for x squared here. And yeah, and now what we are going to try to calculate, this is r squared, is going to be this x squared. So, well, how exactly do we calculate this? There's two ways. You can go ahead and plug in x equals r sine theta cosine phi and integrate, which is not like that long, but it's a bit annoying. Or you can keep in mind that r squared is equal to x squared plus y squared plus z squared. So we would expect that the expectation values here, the expectation value of r squared would be the expectation value of x squared plus the expectation value of y squared plus the expectation value of z squared. But the ground state of hydrogen is symmetric in all directions, right? So that means that all of those three have to be the same. Right? All of those three are the same. There is no preferred direction in the ground state. So it's simply 3 times this. So that means that the expectation value of x squared is simply 1/3 of the expectation value of r squared, which we know is 3a squared, right? So we take 1/3 and we simply get a squared. Okay, so there we did b without having to go through any lengthy trouble. Okay, so now we want to go for part C. So now we want to find x squared, but this time in the state n equals 2, L equals 1, M equals 1. And this time it's not going to be symmetric, so we are not going to have much fun. I'm kidding, doing physics is always fun. Okay, so psi 2, 1, 1, right? What is our wave function this time? This would be, of course, r21, y11, and this you can just look up, right? We have seen in the past many times how we can find it. So let me just write it down for you. This is minus 1 over the square root of pi a, 1 over 8a squared, r e to the minus r over 2a, sine of theta e to the I phi. So I'm gonna move this because we will need a lot of room here. So if we want to find the expectation value of x squared here, we are going to have integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to infinity. I deleted the r there. And now we have to square this thing, so we get 1 over pi a times 1 over 64a to the 4th, and then r squared e to the minus r over a, right? That 2 goes away, sine squared of theta, and this exponent will cancel out because we're not really squaring, we are multiplying by the complex conjugate, so the exponent will cancel out. It is multiplied by e to the minus I phi. And then we have r squared sine theta because we're integrating in spherical coordinates, and then comes x squared. But what is x squared? It is this thing right here. So this time we will just brute force this. So r squared sine squared of theta cosine squared of phi dr d theta d phi. Okay, so I kind of ran out of space here, so I'm gonna delete that. Okay, so what is this? So here, let's see. So the expectation value of x squared, let's take out our constants. So this would be 1 over 64 pi a to the 5th. And that's it. Now let's separate each one of the integrals. So 0 to infinity, this is the radial part. We have r to the 6th e to the minus r over a. And yeah, that's it. So dr. Then we have our thetas. So this would be sine to the 5th of theta. And yeah, that's it, d theta. And then we have 0 to 2 pi of our phi's. So this would be cosine squared of phi d phi. So here what we want to do is integrate each one of them separately. So this one, let's call it IR. That is easy. We already know how to solve it, right? We already saw the formula for it. The formula is, right, 1 over b to the m plus 1 times m factorial. It's exactly the same as before. I mean, it's not the same integral, but it's the same kind of integral, so you can use the formula. So this would be, right, 1 over b to the m plus 1. So this would be 1 over a, or simply a. And m here is 6, so we get 7. And then we have to multiply by 6 factorial. So 6 factorial. Okay, so that's the first integral. Then we go for this, which I'm just going to call I theta, and I phi, which we have not calculated yet. So there's a few ways to go about it. I made an entire video about how to find any odd power of sine, but I guess we can just calculate it manually. So let's begin calculating I theta. Now this integral is of course the one with sine, and well, I made an entire video about how you can find the integral of any odd power of sine, but since this is only 5, it's not that high. I will show you how to calculate this manually in case you don't know that formula that I proved in the other video. I will put it in the description if you want to check it out. So this goes from 0 to pi, and then we have sine theta, and we separate this, right? Sine theta times sine to the 4th, right? So sine theta to the 4th, d theta. But we can write this as sine squared squared. And what is sine squared? It is 1 minus cosine squared of theta. Okay? And here we can use substitution. U is equal to cosine theta, because now we have cosine and its derivative. And du is equal to, in this case, minus sine theta d theta. Okay, so let's plug it in. So here we have minus, and the integral now goes from. So if theta is 0, cosine is 1, and if theta is pi, this is minus 1. And we can use the minus sign outside to reverse the order of integration. So it is now from minus 1 to 1. And then we have, this would be 1 minus u squared squared du. Okay, so now let's just multiply through. So this is minus 1 to 1 of 1 minus 2u squared plus u to the 4th du. And this integral is very, very easy, right? It's simply polynomials. So this would be u minus 2u cubed over 3 plus u to the 5th over 5. And we have to evaluate all of this between minus 1 and 1. So now just evaluating this, we get 1 minus 2/3 plus 1/5. And then we get minus 1 plus 2/3 minus 1/5. So let's see this. We have to take common denominator, so that would be 15. So 15 over 15 minus, that would be 10 over 15 and 3 over 15. And then we get minus, and the same, so minus 15 over 15 plus 10 over 15 minus 3 over 15. Okay, so here we have 18 minus 10, so minus 8 over 15. This is supposed to be a 15. Minus, and then this would be minus 8. So minus 8. Right, so that's, oh, yeah, this is plus 8. So that's plus 8, that's minus 8. So in the end, we get 16 over 15. There we go. So that is 16 over 15. So let's plug it in, right? We just put this right here. So that's 16 over 15. Now the only integral remaining is the phi integral. So the phi integral, I phi, this is integral from 0 to 2 pi of cosine squared of phi d phi. Now this integral is, the main difficulty here is that the cosine is squared. So how do we get rid of our cosine squared? Well, we remember this. We know that cosine squared of phi plus sine squared of phi is equal to 1, and also that cosine squared of phi minus sine squared of phi is equal to cosine of 2 phi. So if we want to write cosine squared in terms of something that is not squared, we just have to add these two equations together, and we get 2 cosine squared of phi is equal to 1 plus cosine of 2 phi, which gives us that cosine squared of phi is 1 plus cosine of 2 phi divided by 2. So we just plug this in here. So instead of having cosine squared, we have 1/2 plus cosine of 2 phi divided by 2 d phi. So this integral now is trivial. The first one is simply u over 2 between 0 and 2 pi, and the second one is going to be sine of 2 phi divided by 4 between 0 and 2 pi. However, it's going to be 0 at both ends, so the only thing that we have left is the first part, 2 pi over 2 minus 0 over 2, so simply pi. So there we go, we have found the last remaining integral. So this thing here is simply pi, so this is pi. So now we can simplify a few things. So of course, this pi will cancel out with this. We have a to the 5th and a to the 7th, so that is simply a squared. And then we have, well, a lot of numbers, so 16 and 64. So 16 times 4 is 64, so this is 1/4. And then let's see, we have a squared times 6 times 5 times 4 times 3 times 2 divided by 4 times 15. Now 5 times 3 is 15. So if we take this and this, we get rid of 15, then we have this. So in the end, this is simply 12a squared. So that is the expectation value of x squared. So yeah, there we go. As you can see, all we had to do was go just slow, steady, integrate, and try to not lose our minds. So I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.